Hi everyone, welcome back to the channel. In today's video, we will be discussing about trees. That's right. So trees are data structures in JavaScript. And in today's video, we'll be looking at how we can implement a tree, and we'll also be discussing the big O notation for the different operations you can carry out using a tree. And without further ado, let's dive in. So, what is a tree? I mean, a tree, come on. Isn't that a plant? Isn't that a living thing? And yeah, I think the analogy of a tree as a plant is synonymous with trees in JavaScript or in programming. So basically, a tree is a data structure that allow you to arrange or store values in a more or less a parent-child relationship. So basically what I mean is in trees, you have nodes, and a node has branches. And just like trees in real life, you have a tree and you have the branches. And a branch has multiple leaves. The same applies to trees. And I think it's best we use a diagram for this. So basically trees are things like this, and things like, let's use this. And this too. So let's use this thing. So basically the tree is something like this. And this has this, and this has this too. Same for this. Take this rest as this, and this too. And let's do this. This things to shoot this, and this. Also, so basically a tree looks like this. So you have your node or your root node, and then you have your branches. So your root node has its different branches. So this is the parent of this and this, and this is the parent of this and this. And the way trees work is that trees usually have a root node. They always start out the root node, and they always have branch. And in trees, you have different types of trees. We have the binary tree, we have the binary search tree, we have a heap, we have trie. There are different types of trees. And this particular tree is a binary tree. And if you notice this tree, if you look at it very well, you'll notice that this has, each of the node has two child nodes. So for this, it has two child nodes. For this, it has two child nodes. For this, it has two child nodes. And when you have a tree that has two children paired to one parent, then know that it is a balanced or a perfect tree. So, for example, for this one, you could see that we have this, and this has children that is this, and this has children that is this and this as well, and it is balanced. And you might be wondering, what does an unbalanced tree look like? So an unbalanced tree looks like So let me show you how it looks like. So let's move this. Sorry. Let's move this. And let's have this. Let's say. And for unbalanced tree, you have things like this. And let's remove this. And you have something like this. So basically, an unbalanced tree can look like this. Basically, what if you notice this tree has 2 children, but this one have just 1 child. And if you look from the pictorial view, it looks so unbalanced. So basically, this is an unbalanced tree, while this is a balanced tree or imperfect tree. Let's say you want to represent these values in trees. So we have something like 12, 3, 4, 2, let's say 0, something like this, for example. So if you're meant to represent this as a tree, of course, the first value becomes 12. So 12 goes here, and second one is 3. So 3 is less than 12. It goes here, and 4 goes here. And 3 is greater than 2. It goes here. Two is less than 3. Sorry, 2 is less than 3, so it goes here. And what's it called? And 0 is less than 2, so 0 goes here. And since we don't have any values here, let's just remove this. So this is how we present this diagram or this value with a tree form. So basically, you place numbers that are less on the left hand side, and then you place numbers that are higher on the right hand side. So that is how you do that in trees. And enough of the talking, let's dive into the implementation of a tree. And to implement a tree, you need to write, or you need to declare your tree node or your tree class, sorry. So you have your tree class, but at the same time, you need to have an idea of what your tree would look like. So trees usually have a left and right node, and these left and right nodes have left and right, like have other branches that could be either left or right. So for that, let's define our node as a class. So as a node class, the constructor looks like this. So constructor, you have like your value. This would have the left value, which is null, the right value, which is null too. And you have, what else? You have your value. That's value. Sorry. So this is how our node constructor, this is how our node constructor would look like. And for trees, our constructor for trees will look something like this. So we'll have our root node, which is root equals to null. Let's use null as the git node. In trees, different operations we can carry out are things like the insert method, that's inserting a tree, inserting a value to a tree, and let's do delete, building a node from a tree. And for this particular video, we'll be implementing this method. And to implement the insert method, first and foremost, we need to write our condition. So if our root is null, then do this dot root equals to a. Let the root is null. Okay, if the root is null, let's add a value. Let's call it, let's say, okay, sorry. Let's just add our value. Let's add our value since I'm using the root, and return our node, and that is for if the root is null. Then then the next condition is then the next condition, before we create the next condition, let's create current node. So the current node should be this dot roots, and you do condition, say if value is less than okay, if value is less than current node dot value, I think this should be think this should be just dot root dot left, right? Okay, sorry, I think we are on the right path. So this condition is for left. So this condition is for the left, and if the value is less than the current node dot value, Then we know that's on the left part. Then we'll do while true. And we'll do while true. Then, so why this is true, we need to do something like this dots. Let's see. While this is true, while this is true, okay. If correct nodes dot left. Small equals to value, then we return else 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 you have current node current node okay, this is good. Then let's implement for right. So if value is greater than current node dot value, then you have try and just change try and try. I think that is it. That is it. I think so. Okay. Let's reduce this so that you can see. Let me increase this to see if it comes better. No, it's not getting any better. Let's reduce. Okay. So so we have our tree now. Let's create a new instance of a tree. So let's say let's call it tree instance. And you do new tree and once you do that, you insert into the tree. So let's insert tree instance that inserts and let's insert let's say 12. Let's say 12. And the next to insert is, let's say 9. And the next one is, let's say, um, let's say 10. And the next one, let's say we have 34. Oh, sorry. Let's insert 34. And next one, let's insert 5. And let's do 40. And oh, I think this is getting. And let's do it. And let's run this. Oh, assignment to constant. Oh, yeah. Oh, why is this? I know it's getting smaller and smaller. Let me try and increase it a bit. How do we do this? How do we do this? Okay, let's just manage this. So yeah, the error was that we were using const here, which is not meant to be. So let's use a let instead. Says we are assigning, or we are changing the value, and let's run it again. Cannot create property left on number 9. Interesting. So what is the problem? Current node constitutes the roots, and let's see. Mm-hmm. Okay, you know what? Let's place the debugger. Let's know what had happened. So let's place it here. And let's run it again. So for the first value, we have our value as 12. That is the initial value as 12. Then have our incoming value as 9. Then if value, which is 9, is less than current node of value 12, which is true, it says if current node dot left, that left is the ball, current node dot left, current node dot left equals to value, and return, right? And insert for 10. If current node of value, okay. Am I meant to return here? That is the thing. Hmm. Okay, let's keep going. So current node dot value. You have your left 9 and you have your value as 10. Then if value is less than current value, which is 10, it's less. Yeah. Oh, oh. Okay. Okay. Current node dot left. Current node. Of course, the current node dot left. I meant to do something there. Let's see. I meant to do something here, right? Ah, correct node dot left. Ah, correct node of current node dot left. And correct node left null. Correct node dot left constant value. Hmm. Oh. Oh. Current nodes dot left dot value. Oh. Oh, okay. 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 Think where the issue is coming from. Okay. 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 I think I know where the issue is coming from. I think I know where the issue is coming from. I think I know now. Okay, so let's clear this. And let's do this. Let's see. So here it's not meant to be value. It's meant to be. I'm meant to do something like new node custom value, and we'll basically just place the cell. Here, current node dot value, current nodes dot left, custom new nodes, and same applies to this. a node and let's run. So you have a tree node and you have the root as the value as 12. Then 12 has a left of 9 and the right of 34. Left has a value of 9 and right is null. Same applies to the right too. So the right has a value of 34 and the right value as 40, which is correct. Which is absolutely correct. Awesome. Yeah, I think that for our tree. This was quite complicated. I know it might probably look complex than you would expect. Let me remove this. Let's see. So I know this might probably look way more complex than expected, but I think you need to take your time to go through the codes to understand what it does. And with that, thank you so much for watching and see you in the next one.